Let's talk about how we can find the average value of a function. If I wanted to find the average of a list of numbers, I would simply add those numbers together and divide it by the number of numbers there are. I could expand this to talking about, instead of particular numbers, I could say, well, let's take a function f and let's look at 4 different points, x1, x2, x3, and x4, and add those together and divide those by 4. I could expand this further by thinking about, let's expand this to talking about adding together n in numbers. Instead of a number such as 4, let's call it n, and I would get something like this. Let's instead think of this as Riemann sums on a specific interval a to b. In that case, my number n, that is the number of items I'm going to add together, is simply b minus a divided by whatever my delta x is. So if I plug that into my formula for my n, now I've gone ahead and used the notation f bar for the average value of x, I could simplify this for my summation times delta x divided by b minus a. I could go ahead and use my summation symbol, and then I can think of this in terms of limits. Let's go ahead and let n approach infinity. When I do that, I can rewrite this expression as f bar is equal to 1 over b minus a times the integral from a to b of f of x dx. So I can now use this generally. My average value of a function on an interval a to b is f bar is equal to 1 over b minus a times the integral from a to b of f of x dx. This is assuming f of x is integrable over the interval ba. If I take this equation and multiply both sides by b minus a, I get that the left-hand side, it looks like the area of a rectangle. It looks like a length times a width, and that is equal to, well, we already know what's on the right-hand side. That's the area under the curve. Let's look at what this looks like in terms of graphs. So again, if I take that average value function, that's a number, and I multiply it by the distance a minus b, and if I multiply it by the distance b minus a, I get the area of that green rectangle, and that is equal to the area under the curve on the right-hand side. Let's look at an example. Let's try to find the average elevation for a walking trail. The walking trail is given by the function 60x to the third minus 600x squared plus 1000x plus 3250. E of x is the distance above sea level in feet, and x is the distance along the trail in miles. And let's look at x going from 0 to 6. I'm going to use the formula I just came up with, that is the average area of E is equal to 1 over b minus a times the integral from a to b of ex dx. When I plug in my equation and do my integration, I find that the average elevation along this walking trail is 2,290 feet. We can expand this to what's called the mean value theorem for integrals. F of c is equal to f bar, which equals 1 over b minus a times the integral from a to b of f of x dx, assuming f is continuous on that interval. What does that mean? Well, in English, that means there is a point c in that interval a to b, where the function actually equals its average value. Let's look at an example. Let's find the point or points on the interval from 0 to 1 where f of x equals x minus x squared equals its average value. The first thing we need to do is find that average value. And we do that by taking this integral and plugging in the limits 0 and 1. And we find that the average value is equal to 1/6. The question is, when does the function equal 1/6? To find out when that occurs, I plug in f of c equals 1/6, and I need to solve for x. I get the form x squared minus x plus 1/6 equals 0. I'll need to use the quadratic formula for that, and when I do, I find two values. X is equal to 0.2113 and x is equal to 0.7887. Let's verify this graphically. When I graph the equation x minus x squared and I draw the line f equals 1/6, I find that in fact that my two x values where that function equals 1/6 is 0.2113 and 0.7887.